5.3, the textbook also discusses concavity. So concavity is when we talk about concave up, concave down. You guys have seen this in your previous math classes. Again, the most basic one is parabolas. This is a parabola that's concave up. And this is a parabola that's concave down. Okay, but in calculus, now that we know this thing called the derivative, f prime, concave up, f is concave up on an interval if f prime is increasing on that interval. Okay, so in other words, if the derivative is getting bigger. F is concave down on an interval if f prime is decreasing on that interval. So same thing, but this time the derivative is getting smaller. So here we have an example of this function that is concave down, then it starts to concave up. So if you notice, we have a positive derivative, positive slope, then it's 0, then it's negative. Okay, if I bring in what I just discussed in that last slide about the it's concave down if the derivative is decreasing, then it's very important to note that, let's say, in order for the derivative to go from this positive to 0, it had to get less positive. So somewhere around here we have a slope that's even less positive than that one, and then somewhere in between here and the slope of 0 we have a slope that's even less positive than that. So that's what it means by the derivative is decreasing, it's getting smaller. Then it reaches 0 and it's still decreasing because then it gets to negative slope. However, this slope here is not as negative as that one. Okay, so then I guess you would say it gets more negative, and it's still, the slope is, f prime is still decreasing. That's why it's concave down by the definition I just said. Same thing here, we have a slope that's negative, but it starts getting less negative and eventually positive. So if we have a slope that's negative here, somewhere here it's even less negative. Okay, so the f prime, the derivative, is increasing. Okay, so it has to get less negative, and then it'll eventually be 0, and then it continues to increase. So there you can see, it kind of helps if I fill in the blanks here and show you how it is that the slope, the derivative, is actually increasing. It's getting bigger. Okay, here's another visual. So less negative, or I'm sorry, here's a slope that's negative, then it's less negative, 0, so, and then it's positive, and then it's more positive. The important thing to note here is that this thing is concave up, but it's concave up because f prime is increasing. Okay, here the slope is positive, less positive, 0, negative, more negative. Okay, so one thing to note is, or the important thing to note is that f prime is decreasing. Okay, I didn't say this, but make sure you're copying this into your notes for your examples. So these last slides that I just brought up, make sure you copy them down as your examples for your visuals. And obviously this one. So just as f prime is greater than 0 on intervals where f is increasing, f double prime is greater than 0 on intervals where f prime is increasing. Likewise, f double prime is less than 0 on intervals where f prime is decreasing. All I'm saying in this little paragraph is that just like we were looking at increasing and decreasing intervals in the last section of the textbooks, we are going to look at the double prime where it's positive, where the second derivative is positive. That's where my derivative is increasing. Where the second derivative is negative, that's where f prime or derivative is decreasing. This is the important part here though. So if that little paragraph that I just tried to explain confused you, just pay attention to this. If the second derivative is greater than 0, in other words, if the second derivative is positive on an interval, then f is concave up on that interval. If f double prime is less than 0 on an interval, then f is concave down on an interval. So this is exactly what I was trying to say. I was trying to say that just like how we were using the first derivative to see where we were increasing or decreasing, whether the first derivative was positive or negative, this was all from the last section of the textbook of the chapter. In this section, we're going to look at the second derivative. When the second derivative is positive, we're concave up. Second derivative is negative, we're concave down. Something that comes with concavity is a point of inflection. If c comma f of c is a point of inflection, then either f double prime of c is equal to 0 or f double prime is undefined at x equals c. This implies that the f double prime of x changes from positive to negative or from negative to positive at x equals c. So these are some important things to note from this. I'll show you an example right now. Let's just copy this down for your notes. And this is what a point of inflection looks like. It's, in other words, a point of inflection or inflection point happens when you change concavity. Okay, so it changed from concave down to concave up. So this point is the inflection point. From concave up to concave down. Okay, this is the point of inflection. And here from concave up to concave down. Okay, so let's look at some examples. Let me write it down. So determine the open intervals on which the graph of f of x equals 6 over x squared plus 3 is concave upward or downward. So if we're talking about concave up or concave down, instead of the first derivative, the second derivative should come into play. So just like we were doing it with increasing and decreasing values using the first derivative, intervals, not values, increasing or decreasing intervals using the first derivative, we are going to use the second derivative. So find f double prime. And we're going to use the second derivative to determine whether we're concave up or concave down. So right now, go ahead and pause the video and you try to find the second derivative of this function and check it with mine. So pause the video. So for the first derivative, I got negative 12x over x squared plus 3 squared. So notice that I did a little trick that I've been forgetting to bring up, but I have noticed that some of you guys have caught on to this trick. Is 6 over x squared plus 3 can be written as 6 over x squared plus 3 to the 1. And if I bring this up to the top now, it becomes a -1. And I can avoid using the quotient rule here and instead use the chain rule. So using the chain rule here, just follow these steps, and don't forget to take the derivative of the inside, which is 2x, x squared plus 3, the derivative is 2x, and you should get the same answer after you've done maybe some rearranging. So if you use the quotient rule, you should have still gotten this answer. For the first derivative, this is f prime, and then for the second derivative, so this negative 12x kind of prevents you from redoing that same trick. If you send this to the top, now you have to use the product rule because of this x here. So that was a nice thing about the original function not having a variable in the numerator. That's how we were able to use this trick. With this one, we can't really do it without having to use the quotient, the product rule. So instead, I'm just going to use the quotient rule, and I got f double prime is that. So now, just like in the last section, kind of like finding critical numbers, but these aren't critical numbers because it's the second derivative. But we are still going to set the numerator equal to 0. So step 2, we want to break this down into steps, is do the numerator 36 x squared minus 1 equal to 0, and the denominator x squared plus 3 cubed equal to 0. Okay, I'll let you guys solve this. I'm going to pause the video. You guys pause the video. Okay, so hopefully you got these x values. X equals plus or minus 1, so x equals positive 1, x equals negative 1. For the denominator, the square root of -3 would consist of imaginary numbers, and I just want to remind you that there are no imaginary numbers in calculus, so we go ahead and ignore that and just focus on these. And the next step will be you guys plug this into the number line. So step 3, and you're going to go ahead and choose some test values. So the f double prime number line. Okay, so we have -1, +1, and pick some test values like, I don't know, -2. Pick a test value here. A nice one between -1 and +1 is 0. If you can use 0, always use 0 as a test value, and +2. So we're going to plug these into the second derivative. Okay, so f double prime. Of -2, f double prime of 0, and f double prime of 2. So go ahead and pause the video and work these out on your own. Okay, so you should have gotten concave up from -infinity to -1, concave down from -1 to +1, and concave up again from +1 to +infinity. So these are the signs. I didn't really do the work. I just showed you the outcomes. They should have come out positive, negative, positive. So one thing I want you to notice is that because the signs change from positive to negative, -1 is also a point of inflection. It changed from negative to a positive at +1. It just happens that both of these happen to also be points of inflection. I want you to notice that it's because the signs changed from positive to negative and from negative to positive. So your answer should look more like this, because it didn't really ask for the points of inflection. I just decided to throw them in here, and the graph for this should look like that. Okay, so we can see that at +1 and -1, well, we ran out of time, but that was the graph and the points of inflection. That is it.